I really like this.
Oh, hi, Anna. Are you ready?
Yes, I'm ready.
Okay, so maybe we can start now. And so today, our first speaker will be Anna Wienhard. The title is Positivity, Higher Teichmüller Space, and a Non-Commutative Class Algebras. So please.
And thank you very much. And I would like by thanking the organizers for putting together this very interesting conference. And for me, it's really an honor to speak here. I'm very sorry that I cannot be in person with you at Yale. And I hope that I will see many of you in the next year at other occasions. So before I start with my talk, I want to tell a bit about my connection to Sasha. So the first paper I actually read or tried to read by Sasha had nothing to do with higher Teichmüller spaces, but was really on block regulator map and related to bounded cohomology. And then somehow I got more contact and interaction with Sasha through higher Teichmüller theory and higher Teichmüller spaces. And I really learned a lot from him and different points of view on things, and always found him to be very supportive. So I vividly remember one incident where I was visiting Yale as a young assistant professor from Princeton, and it was the first research visit I did, being somehow visibly pregnant with my first daughter. And so of course, when I was a bit insecure to see what people think or how they react, and I was meeting Sasha, and we were just having a great math conversation, and then said Sasha and Volodya Fogg were in the process of organizing a spring school in Jerusalem, and said, why don't you come and you can bring your daughter with you? And it was a very great, somehow very supportive experience at that stage of my career. So what I want to tell you about today is I want to start with reviewing some of the aspects of the work of Fogg and Goncharov on higher Teichmüller spaces, and then but in a perspective to generalize these aspects of the work and how they fit together with other somehow examples and of higher Teichmüller spaces where we know to some extent much less than what we know in the cases Volodya Fogg and Sasha described and proved a lot of things on. So let me start by in some sense recalling very broadly the aspect, the setup and of their work. So you have a complex Lie group and G and a topological surface with puncture, or more generally with boundary and puncture. And you are interested in the space of G local systems on the surface. And then in their paper, Fogg and Goncharov introduced two other moduli spaces, which are not the space of G local systems, but which sit partly above them, namely the space, the X space, which is the space of framed local systems. So where over the puncture, you endow your local system with additional information, namely a section of the flag variety G mod B. And the other space, the A space of decorated local system, where you actually look at not just a section of the flag variety G mod B, but of the affine flag variety G mod A. And then on these spaces, you can construct coordinates by fixing an ideal triangulation, or more generally, a more complicated triangulation or quiver on the surface. And I want to describe in the simplest case, recall you on the next slide, how you get these coordinates. And then one very important aspect is if you look at coordinate changes when you change the triangulation of your surface, so your coordinates depend on the triangulation, but when you change your triangulation by a flip, the coordinate changes are given by positive rational functions, or actually more explicitly by cluster transformations. And so what you get out of that is that the positive real loci of this X moduli space and the A moduli space is well defined up to, independent of the ideal triangulation. And since for what I want to tell you later, in some sense, the simplest case is the most relevant, let me recall how you get coordinates in the case when you look at an SL2 or PSL2 local system on the surface. And so let me just take the one puncture torus. We pick an ideal triangulation of this one puncture torus. So we have this two triangles where sides are identified. And now let's look at first the X space. In order to look at the X coordinate, we have a framing over the puncture by RP1. So which means that if we want to construct coordinates at every vertex of our triangulation, we have a line in, so I now describe it just for the real point, but in general, you can do it on CP1, a line. And then we can associate to an edge of this quadrilateral the cross ratio of these four lines, which we see at the four edges of the quadrilateral. And if you really look in SA2R, this is very similar to shear coordinates, which have been introduced by Thurston and Bonneau. So when you do A coordinates, you have a different decoration because, now the decoration at your vertices is not just by line, but actually by vectors. And you are in SA2R, so you have a symplectic form, which is preserved by your group. So you have your symplectic form on your two-dimensional vector space. And so now you can endow this edge with a coordinate, which takes one vector and the other and pairs them by the symplectic form. So for this, for a quadrilateral, now you don't need to know any information about the decoration at the other two vertices. It's really just at the vertices of the flags. Okay, so now what happens if you change the triangulation? So then you get these very well-known cluster transformations. So when you do a flip in your triangulation and you look at how the coordinates, before you had coordinates A, B, C, D, and X on the edge which you flip, and then you have coordinates A prime, B prime, C prime, D prime, and X prime on the new edge which you introduce, how the coordinates change. Then you have this formula for the X coordinates and the Ptolemy equation, or very basic cluster transformation for the A coordinates. So now what I want to describe, when you generalize in the generalization of the work of Fock and Goncharov, the coordinates are very closely related with total positivity and total positive semigroups. And I want to describe this shortly. So it really relies on the generalization of total positivity for any split real Lie group introduced by Lustig many years ago. And let me just give you somehow basics again, only on the aspects I want to focus on. So there's much more to this story, of course. So you start with a split real Lie group. You look at delta, the set of simple roots. You have the Y group. You look at the Borel group, maximal torus, and the unipotent radical of the Borel group. And now you can introduce a semigroup in this unipotent group in the following way. So you consider the root spaces for all the simple roots, and you pick Chevalier generators, for example, for your Lie group. So E alpha, F alpha, and H alpha, such that they E alpha, F alpha, H alpha satisfy the SL2 relations. And now you take the sub semigroup of U, which is generated by taking positive, and here I forgot to say that T has to be positive. So you take positive multiplets of your generator, and then you take X, so you get an element in the unipotent group, and you take the entire semigroup generated by them. So this is the non-negative semigroup. If you want to get the positive semigroup, you have to be we have to work a bit harder, and you get it by giving an explicit parametrization of this set as a subset of the unipotent radical. For this, you pick gamma, a reduced expression of the longest word in your while group. So it's some product of the reflections in simple roots in delta. And for each reduced expression, you define a map which depends on the reduced expression from the product of all the root spaces corresponding to the roots, of which this is the associated reflection, into your unipotent group U by just taking this n tuple of vectors and sending it to the product of the exponentials of this vector. And now if you do this, take this map and you just evaluate it on the positive reals of your Chevalier generator, you get an image, and Lustig showed this image is independent of the reduced expression you choose. It actually has the structure of a semigroup, and this is what you call the positive semigroup in the unipotent radical of the Borel group. When you do this for GR being GLNR or SLNR, then I mean you can arrange your Borel to stabilize a standard flag, and so you can write the unipotent radical as the upper triangular matrices with ones on the diagonal, and the conditions you get for an element to lie in this positive semigroup is precisely the condition you have in total positive matrices in GLN, that every minor that is allowed to be non-zero, since you are upper triangular, you're unipotent, is actually positive. So if you have this positive semigroup, you can use it to introduce positive configurations or positive n tuples of flags. And this plays a, I mean, this plays a very important role in Fock and Gontchalm's work. So I just describe it in some sense for GLN, but it's clear how to generalize it. So you take the full flag variety. If you have a triple of flags, where I assume that F0 is the standard Borel, F infinity is the opposite. Sorry, I take F infinity to be the Borel, F0 to be the opposite Borel subgroup, then I can always write a flag which is transverse to F infinity as the image under F0 by an element in the unipotent radical of the stabilizer of F0. And I say that this triple is positive if this unipotent element is not just in unipotent radical, but actually in this positive semigroup. So for a GLNR, I can just think of this as being, again, upper triangular matrices with ones on the diagonal. And so the triple is positive if this is a matrix, unipotent matrix, upper triangular matrix with one on the diagonal where every minor is positive. Can do now the similar thing for four tuples, where, I mean, you write, you take again F0 to be the opposite Borel, F infinity to be your chosen Borel subgroup, and then you write F1 by as image of a unipotent element of 0, F2 in the same way, and if you can write UF2 as U times F1, and all these three elements are in the positive semigroup, then you have a positive four tuple. And if you, I mean, geometrically, it has a very nice picture, and this is something which again I learned through the work of Fock and Gontchalm, is that if you look at R equals n equals 3, so you are in GLN3, you look at the flag variety, which you can, it's a point and a line, so I can think of it as a point in projective space and a line through that point. Then that a four tuple is positive means that it actually bounds a convex domain in its interior. So if I draw this picture of the four flags, I can find a convex, strictly convex domain, which is such that these four flags arise at the boundary of this domain. And I mean, having this positive semigroup, there is of course some very natural generalization of the notion of positive triples and positive four tuples, and more generally positive n tuples in the flag variety, your split real group modulo the Borel for any split real group GR. And so this is, you can use this structure to now understand more geometrically what actually is the locus of a positive G local system. So if you come back to the situation which I described on the first slide. We have a complex Lie group, we have our punctured surface, we have this X moduli space, the A moduli space, which we can put coordinates on depending on a triangulation or more generally a quiver on the surface. And the positive points of these varieties are well defined. And then I can ask, if I forget about my decoration and my framing and I just project to the space of local systems, what is the local system? What are the local systems which I get? And one way to describe this is using the positive structure on the flag variety. For this, one has to first realize that you can, if you look at the fundamental group of a surface, you can pick any, say, hyperbolic structure on the surface, so that you realize of infinite volume if you have punctures. You want this, so basically take a discrete, nice discrete faithful embedding of pi1 of s into PSL2R, such that every element goes to a hyperbolic element situation, and you get the set of fixed points of the fundamental group of the surface in the boundary of the hyperbolic plane, which is RP1. And this fixed point naturally comes with a cyclic ordering. And actually, the way that, the cyclic ordering does not depend so much on the way you represent your group. So now, if you have this set with the cyclic ordering, you can make the definition of positive maps from the cyclically ordered set into your flag variety by asking that every n tuple, which is cyclically ordered, is sent to a positive n tuple in the flag variety. And so now if you have a representation from the fundamental group of your surface into your split Lie group, you can say that this representation is positive, and this is the definition Fock and Kontraf give in their paper. If there exists a row equivalent map from the cyclically ordered set into the flag variety, which sends positive n tuples in the sense of cyclic orientation to positive n tuples in the flag variety. And this is now, one has to be a bit, I should be more precise, making the distinction between x coordinates and a coordinates, but I don't want to do this here. But basically, then what one of the things Fock and Kontraf show in their papers, that the set of positive representations, so just really the local systems which correspond to the positive points of the X variety, is precisely a set of positive representations in this sense. So as admitting a row equivariant positive map to the flag variety. And now I want to make one important observation, which that this, what I described so far, really the coordinates, getting the coordinates and getting these cluster transformations when you change the triangulation, this really depends on having a punctured surface, having at least one puncture or at least one boundary component. But this characterization in terms of positive maps here, this is something which makes complete sense also when S is a closed surface. Then I can, when S is a closed surface, I have my fixed point of element of pi1 of S in RP1 the same way, and I can ask for representation to be positive in this sense, without having any coordinates at hand, but using this notion of positivity in the flag varieties. And this is, in some sense, really also for me was the starting point where what I was thinking about and what I was interested in 20 years ago or so, to make connection with the work of Fock and Kontraf, because what I was interested in was more the situation of closed surfaces, so surfaces without boundary, and the observations that there were several connected components in the space of homomorphisms of the fundamental group of a closed surface into special real Lie groups G up to conjugation, which consists entirely of discrete and faithful representations. So this is one, if G is as a PSL2R, this is one way to characterize the Teichmüller component. So it's the only component or up to orientation, changing the orientation of two components, which consists entirely of discrete and faithful representations of your closed surface group. And there were two other cases which were in some sense introduced earlier, but then discovered that they have this property, that they consist entirely of discrete and faithful representations around the same time as Volodya and Sasha did their work on higher Teichmüller spaces, namely what is called the Hitchin component and what is called the space of maximal representations. And so let me first focus on describe shortly the Hitchin component, because this is really the component which connects to Sasha's work. So whenever you have a split real D group, you can look at the principal three-dimensional subgroup in G. So this is a specific embedding of SL, gives you a specific embedding of SL2R in your group G. And if you compose it with a discrete embedding of the fundamental group of your surface into SL2R coming from a hyperbolic structure, you get one representation into your split real Lie group. And then what Hitchin basically showed that if you look at all the deformations of this representation, this is a connected component by definition. So you look at the connected component of this containing this representation in the representation variety, but it's actually homeomorphic to a vector space. So it's homeomorphic to a vector space of dimension 2G minus 2 times the dimension of G. And when Hitchin introduced this in the 90s, he didn't have any information about geometric properties of representation in this set. But then shortly after, Goldman and then Choi-Goldman showed that actually for n equals 3, everything in the Hitchin component is a discrete and faithful representation, and actually also is related to an interesting geometric structure similar to hyperbolic structures on surfaces. And then around 20 years ago, Labourie proved that for the classical groups here, the first classical groups, anything in the Hitchin component is a discrete and faithful representation and actually has more geometric properties. And also Fock and Gontcharov in the work, using this characterization in terms of positive representation, actually showed that if you take something in the Hitchin component, this is precisely the set of positive representations of this closed fundamental group of this closed surface into your split real D group G. So the Hitchin component really is the somehow closed surface counterpart to positive, or is really the set of positive representations for a closed surface. And so what I described to you before in the punctured case, on this side of the story, we have this very interesting connection to total positivity, to cluster algebras, and to work of Gayotto Moore-Naitsky, and there's also to physics. So now what I want to talk about a bit more is the right-hand side. So when you look at not split real Lie groups, but real Lie groups which are of Hermitian type, so which means that these are real Lie groups such that the symmetric space you associate to them actually has an invariant Kähler form. So they can also be characterized that if you look at these, if you look at the maximal compact subgroup in here, this is not semi-simple, but has in the simple case where this is simple, has a one-dimensional center. And so for these groups, you have, for representations of the fundamental group of your surface into this group G, you have a characteristic number, which is often called the Toledo number. And you can look at this Toledo number satisfies bound. So it's in absolute value bounded by 2G minus 2 times the rank of G with the right normalization. And you can look at the subset where this characteristic number assumes its maximal possible value. If you do this for SL2R, so in the rank 1 situation, so for SL2R, then by a theorem of Goldman, you get precisely, again, back the Teichmüller component. But if you do it for Lie group of higher rank, so for example, for the symplectic group SP2NR, you get actually not one connected component, but you get several connected components where this Toledo number assumes its maximal value. And in joint work with Mark Boger and Alessandro Iozzi around the same time, 20 years ago, we showed that every representation in this component of maximum, in these components of maximal representation is actually a discrete and faithful representation. So from some point of view, the situation looks very similar. You have these connected components consisting entirely of discrete and faithful representation, but from other situations, it's a bit different. Here you have the section to the Hitchin fibration, you have one connected component, you have several connected components, and the connected components have non-trivial topology. And what was a question which was very intriguing to me for many years is to see, I mean, on the side, as I described for Hitchin component, because these are precisely positive representations in the sense of Fock and Gontard, we have this link to total positivity, to cluster algebras, and also interesting connection to physics, which on this side of the picture, we don't really know. And what I want to tell you now a bit about is that actually now we know that there is some interesting connection to positivity and also interesting connection to cluster algebras. And I want to describe this a bit. We don't know yet, and I come back to this at the very end. We don't really know yet very precisely what the connection to physics is. Okay, so to describe some of the story for the right-hand side of maximal representations, and actually for a bigger class than just these maximal representations, I want to introduce a generalization of total positivity, which now applies to this setting where G is a simple real Lie group, non-compact, but not necessarily split. So I mean, when you look at the example here, for example, it would apply to the group SUNN here, which is not split, but of Hermitian type. It also applies to the group SP2NR, but this, of course, is also split Lie group, would apply to SO2N, but also some other families of groups. And so the idea is that we try to do mimic, in some sense, a lot of the construction of Lustig for total positivity. So we pick our Lie group, we have the set of simple roots, and now we don't take the minimal parabolic subgroup, but we really give us the freedom to choose a parabolic subgroup. So we take a subset of the set of simple roots and the corresponding parabolic subgroup, P theta. We look at its Levy subgroup and its unipotent radical. And now we do something similar, like decomposing in the split case, the parabolic, the Lie algebra of the parabolic subgroup or of its unipotent radical as a sum of root spaces. But now we decompose it not in the sum of root space, but we decompose it as representations of this, the connected component of the Levy group. And if you do that, you see that you have different pieces, and the simple pieces, so the pieces which would correspond to the simple root spaces in the split case, are precisely pieces which correspond to the roots alpha in your subset theta of the space of simple roots. Now we'll give you a bit later an example where you can see how such a piece looked like. And now, in order to somehow define what we mean by a positive structure or theta positive structure on our group G, we want to require that in each of these simple pieces U alpha, this is a representation of L theta, the connected component, that we find a non-trivial acute convex cone in this subspace. This is now not a root space, it's in general of higher dimension. So, but we require that we find an acute convex cone in this subspace. And this now, I mean, you will see on the next slides that actually from this we get a lot of structure. But the first thing is that if you require that, you can actually, by looking at the Dinkin diagram of the reduced root system of this real Lie group, you can classify in which situations you can satisfy this condition. And there are exactly 4 families with then appropriate choices of theta. So the first family is a split real Lie group where theta is the set of all simple roots. And so the parabolic is the minimal parabolic, so it's the Borel group. And in this case, all the pieces U alpha, alpha, and delta you have would just be the simple root spaces. So this is really puts us in the setting of Lustig total positivity. Then the second family, and this is a family of Lie groups you already saw on the previous slide from maximal representation, is when we have a Hermitian Lie group and a specific one of tube type, which is if you have a Hermitian Lie group and you look at the reduced root system, there's one family for this, for which the reduced the reduced root system of our roots is actually reduced as a root system, and one where it's not. And these are the family where this is reduced. So it's a CN reduced root system. And in this case, you take theta to be just a subset consisting of one specific root, and theta the corresponding maximal parabolic. Then there are two other families which we somehow didn't necessarily expect to arise. And one is the groups which are SOPQ with P less than Q. So I would you could take the connected component here. Theta is almost the full set of simple roots. You just remove one specific root and you remove the root such that the corresponding parabolic has the description as the stabilizer of a partial isotropic flag, where you forget about the p, the last, the biggest dimensional flag subspace. And then there's a fourth family, which is basically all the real Lie groups where the reduced root system has an F4 Dinkin diagram. And these are real forms, specific real forms of F4. So the split form of F4 and then real forms of E6, E7, and E8. And there, this subset theta you can take, it consists of two roots, alpha 1 and alpha 2. And I draw a picture where you see more precisely how the subsets look like on the next slide. So these are again the four families. So we have split real form with the minimal parabolic, and we just have the standard set of simple roots. We have this Lie groups of Hermitian type of tube type. The reduced root system here is a CN root system, and the root you take is the one which has, it's long one, so which has a double error to the others. And then for SOPQ, the reduced root system is BN, and you take precisely the opposite set. So you take the all the P-1 simple roots, the short ones. And then you have the F4, so where you have this kind of root system, again, you take the two such that the set theta is connected to the complement of theta by a double arrow pointing to the complement. And so in all these situations, when we look now at the structure which I started with, so the decomposition of the algebra of the unipotent radical of my parabolic group P theta here as a representation under the Levy component, then you see that, for all the roots in theta which are not connected to the complement, you will get that U alpha is G alpha. But for this special root, which I now call alpha theta, so this is the special root which is connected, the root in theta, the unique root in theta which is connected to the complement, will have the dimension of this space U alpha theta is actually of dimension bigger than 1. And what it is, it's the sum of all the root spaces which basically modulo the complement of theta are equal to alpha theta. So all root spaces which are of the form alpha theta plus roots in delta minus theta. So what plays an important role now when we want to use this setup to define non-negative and positive semigroups is a subgroup of the Y group. So we saw that for the positive semigroup, in the unipotent radical of the Borel group of a split Lie group, what played a role was the Y group and reduced expression of the longest word in W. So here, in some sense, the Y group, which governed the combinatorics there, is replaced by what I want to call the theta Y group. And it's a subgroup of the Y group of G, generated as followed by the following elements. So if you are not, for all the roots which are in your subset theta, which are not this special root, alpha theta, you just take the standard generator of the Y group. So you just take the standard reflection associated to the simple root. But for this alpha theta, you take an element of your Y group, which is not the standard generator, but it's a longer word in your Y group. Namely, you take a representative of the coset of the longest word in this Y group. So the Y group of which we would get from the root system, taking alpha theta plus its complement. So this here would be right, alpha theta everything. Here it would be alpha theta plus the complement. So it would just be these two roots, and here alpha theta plus the complement would be these three roots. So you take the longest word there in the coset mod the Y group of delta minus theta. And now the first, I mean, this is just a subgroup of your Y group. You can show it's, I mean, it's a nice Coxeter group, but actually what turns out is that it actually is a Y group of a different type than the Y group of your group G. And I will illustrate this on the next slide. I just want to give you an example in the case when we are SOPQ, right? And so we, for this alpha, the P minus first root, we have to take this special element to generate the theta Y group. And I mean, it's the longest element in this, we would take the longest element in this B2 root system. So this would be SP minus 1, SP, SP minus 1, SP. But we take a representative of the coset mod SP. So we have a word which is SP minus 1, SP, SP minus 1. Okay, so let me just illustrate on this slide or give you what is the theta Y group. I mean, it's in the split case, sorry, in the split case, we just have the standard Y group. We don't change anything. In the Hermitian case, we just have this single piece U alpha. So our Y group is generated by a unique element. This is an element of order 2. So we get the Y group, which is a subgroup which is isomorphic to the Y group of an A1 root system. In the case of SOPQ, where we have, I mean, this BP root system, we have the Y group, this theta Y group will be generated by the standard generators for this P minus 2 root. And for the P minus first root, we take this longer word, and then you can check on what, I mean, the relations and everything, and you see that the theta Y group is actually the Y group of a BP minus 1 root system. And if you do it for F4, we have two generators of this theta Y group, and you can check that it's actually the Y group of a G2 root system. And so let me say in quotation marks, heuristically, many things that work for total positivity work for these groups admitting a theta positive structure in a similar way when you replace the Y group by this theta Y group. And now I want to illustrate this in one example, namely to give you the definition of what this theta, what in this theta positive case, what the positive semigroup will be. And for this, we use the theta Y group in a similar way as we use the Y group in the split case. So just, I mean, so we keep the setup. So we have a simple Lie group. We have this set of simple roots. We have this subset of the set of simple roots we chose, and we have in each, so then we have the corresponding unipotent radical of the parabolic subgroup associated to this set of simple roots. And then we assume that in each of this U alpha, the pieces of the simple piece of the Lie algebra, we have this convex cone, which is invariant under the connected component of this Libby group. So this is the C alpha. And taking these convex cones, we now can define a non-negative semigroup, just as the subgroup, sub-semigroup of U theta, which is generated by elements which are just exponential of images, elements in this cone. So this now gives us the non-negative semigroup. And in order to define the positive semigroup, we do basically the same thing than what we did in the split case, but now using this theta Y group. So we take the longest element in this theta Y group, we write down a reduced expression. So this reduced expression, in terms of our generator sigma alpha 1 to alpha k, where alpha k is this special alpha theta, is a word in these generators. And for each of the sigma alpha I, we have this corresponding piece of the unipotent, the Lie algebra of the unipotent radical. We take the product of all of them, and we send a vector vi1 to vin to the product of their images under the exponential map. And then you can show in a very similar way, but actually there are two ways to show that the image of this map, if you evaluate it on the interiors of the cone, these closed convex cones you have, you evaluate it on the interiors, the image is actually independent of what reduced expression you choose. And it's in semigroup, it's invariant under the non-negative semigroup. And it has also the nice property that actually this positive semigroup is a connected component of the Brouillard cells associated to p theta and p theta. And so I wanted to give you one example of how this u alpha theta looks like when it's not just a simple root space of a simple root. And I mean, here's one case when we take the symplectic group. With the symplectic group, we can look at the split Lie group, but now I want to look at it as a Lie group of Hermitian type. And then its theta positive structure would be related to theta, the subset, which is just one root, and it's the root such that the parabolic associated to this root is a stabilizer of a Lagrangian subspace in your symplectic vector space. And then this u theta, which will be, here we just have one piece, right? We have just one simple piece. So we have u alpha theta will be just the space. You can identify it with the space of n by n symmetric matrices over the reals. And the convex cone you have in here, the interior part, will just be the positive definite symmetric n by n matrices. And so in this case, this map is very easy because our bi group was just an A1 bi group. So we have the longest element is just one generator. So it's we just have one piece. So we send the positive definite symmetric matrix to the matrix identity M0 identity, where M is a positive definite symmetric matrix. But in general, so when you look at the SOPQ case, of course, you have longer expressions here. You have more complicated, more complicated maps. But now we have this theta positive semigroup. So we have this u theta positive, and now we can do in a very same way as I introduced before the notion of positive triples or positive n-tuples for the split real case in the flag variety G mod the Borel. Here I can use the notion of positive triples and positive n-tuples in the flag variety G mod p theta. So it's basically, it's really the same. So I look at p theta up, and I have a third parabolic with p. I can write it as an element of the unipotent of p theta applied to p theta up. And if this unipotent is in my semigroup, then I call this triple positive, and similar for the four tuples. So with this, you can now also make the same definition of what a positive or theta positive to make to keep track of what positive structure you use. A theta positive representation is, so if you have a group G which admits such a theta positive structure, then you call a representation of the fundamental group of a closed surface, or you can also take a surface with punctures. Positive if you have this row equivalent map, boundary map from this cyclically ordered set of fixed points into your flag variety G mod p theta, where positive again means you take a cyclically ordered n-tuple and send it to a positive n-tuple of flags in G mod p theta. And then you actually can see that from a lot of point of view, these things are very similar to the things we saw before, to the set of maximal representations or Hitchin components, which are some positive representation, which are the most sub-examples of that. And you can show that whenever you take such a theta positive representation, it gives you a discrete and faithful embedding of your fundamental group of your surface into G. It actually has a bit more properties, finer properties and dynamic properties, which is that it's theta nosov, but I don't want to explain what this means. But it has one consequence, that this theta set of theta positive representations is open in the representation variety. And then when S is a closed surface, you can actually also show that in many cases, we don't know yet if in all cases, but in all these four families, there are connected components of theta positive representations, which actually gives rise to higher Teichmüller spaces. So where this set is not just open, but it's actually closed, and it gives rise to connected components. And I mean, there's, which I don't want to go into detail, but I strongly believe that these higher Teichmüller spaces, in the sense that you have for a closed surface connected components of the representation variety, which consists entirely of discrete and faithful representation, exist precisely in these cases where your group G admits a theta positive structure. Okay, so now I want to somehow perhaps go back to this slide. But so I basically told you that having this generalization of total positivity, you can see positive representation in Fock-Goncharov sense and the Hitchin component as the situation for the split regroup, maximal representations as the somehow corresponding picture in the case where G is Hermitian, and there are actually two other somehow interesting families of higher Teichmüller spaces which arise for SOPQ and G. So now what I want to go in the direction of is now what is about the things which we saw and which we know from the work of Fock and Goncharov on cluster structure, on interesting coordinates on X space and A space. Do we have a similar picture also in these three cases? And I really want to look at the simplest case, which is the simplest case in this family, where I have a Lie group of Hermitian type, where I look at the maximal parabolic, and where this Y group, which governed all the combinatorics I used to define the positive structure, it's actually very simple because it's just the Y group of an A1 theory. What I want to show you that in this case, we can actually make it very precise that this the space of maximal representations and or also these Lie groups of Hermitian type of tube type are really like an A1 non-commutative A1 theory. So I want to do this by telling you first about some of the picture of coordinates when we look at representations in a Lie group which is Hermitian of tube type, and I really want to describe it in this example for SP2NR. So we look at the Lie group SP2NR, but now don't want to look at it as a split Lie group, but with its positive theta positive structure coming from this maximal parabolic, which was the stabilizer of a Lagrangian subspace in R2. So then you can introduce, if you have a local system, an SP2NR local system, you can introduce in some sense a related X space and related A space by looking at now framed local systems, but where the framing is now not by something in the full flag variety for the symplectic group, but just by something in the space of Lagrangians. And for the A coordinates, you would frame by somehow decorated Lagrangian, by Lagrangian together with an isotropic basis of n isotropic vectors, which form a basis of your Lagrangian subspace. So now you can use this framing to construct coordinates. So these now look a bit more complicated than in the SA2 case, but the combinatorics, I mean, if we think of this should be an A1 non-commutative theory, the combinatorics should just be like in the SA2 case, just associated to a triangulation and not a more complicated quiver or subtriangulation of the surface. So if we take this one punctured torus case, we take a triangulation of the surface. We now have, if we see a quadrilateral, we have it decorated by 4 Lagrangians at the corners. And now you can have to do the first thing, which in the SA2 case you don't have to do, but in the, I mean, in the symplectic case, SP2NR with n bigger or equal than 2, 3 Lagrangians have an invariant in real space, namely you have the Maslov index of 3 Lagrangians. It's a discrete valued invariant, but this is in some sense invariant you have to plug into the to the triangles. Then for each edge, you have something like a cross ratio, and the cross ratio is now a symmetric endomorphism of L0, if you want, which is well defined only up to the action of the stabilizer of these of this triple of Lagrange and this triple of Lagrange. And then if you want to not really, I mean, if you want to take not this equivalence class, but take representatives of the equivalence class, you can take a representative of the equivalence class, but then you have the problem that if you pick a representative for this edge and a representative for this edge, you might represent them in different bases, and you have some kind of change of basis for the corners. So in the simplest case, where you look at a situation which corresponds to maximal representations, these Maslov indices, they will all be n by maximality. So in some sense, you can forget about this invariance. And then here for the cross ratio, we have a symmetric matrix up to the action of On. So you can represent it by a diagonal matrix. And then for each corner, I mean, for each angle, you have an element, basically an On in the generic case, which describes the change of basis from the basis which diagonalizes this symmetric matrix to this basis which diagonalizes this symmetric matrix. And so if you go around once, you have this relation. So this might look a bit complicated. So X coordinates look a bit complicated, but there's in some sense no way to simplify it right away. So if you want to, I mean, there's a way to simplify it by over-parameterizing the space. And if you over-parameterize the space, you basically can associate to every edge just a symmetric n by n matrix. But I don't want to describe this detail. I really want to focus on the A coordinates. The A coordinates are much simpler. So the A coordinates, I mean, also in the SA2 case, were much simpler because they only depend on the two Lagrangians at the end of the edge we look at. And so here, at one edge, we have a Lagrangian together with a basis of this Lagrangian subspace. And on the other side, we have a Lagrangian with a basis of this Lagrangian subspace. And we have at our disposal our symplectic form. So we can build a matrix, which is taking omega of the ith basis vector. I mean, the ij entry is omega of the ith basis vector of this basis of this Lagrangian and the j basis vector of this Lagrangian. And with this, we get the matrix. Of course, this depends not just on the edge, but actually on the edge with an orientation. If we change the orientation, we get minus transpose. So with these A coordinates, you can actually, so this is what I just said, if we change I and j, right, we change the direction of the arrow, we get minus the matrix transpose. So then you can, in the A coordinates, you can compute what is actually the flip. And you get a very nice formula for the flip, which is like a non-commutative Ptolemy equation. And you actually get also by, you get triangle conditions for the matrices which arise at the edges of a triangle. And if you look at these relations, these are actually precisely the relations which appear in Bernstein and Drettak's work on non-commutative cluster algebras or non-commutative marked surfaces. And so you get, by building these coordinates for symplectic representations, you get, in some sense, a geometric realization of Bernstein and Drettak's non-commutative cluster algebra. And I want to somehow emphasize again that this really looks like a non-commutative SA2 theory. You have the same combinatorial structure, the triangulation of the surface, just you have an coordinates associated to the edge, which are not one by one matrices, but n by n matrices, and so things don't commute anymore. But it's really like a non-commutative SA2 theory. And now I want to, in the remaining few minutes, tell you that actually it's not, you should not think of this as a non-commutative SA2 theory. It's better to think of it as a non-commutative SP2 theory. So where you don't think of R2 with a determinant, but where you think of R2, having space R2 with a symplectic form, and look at the group of symplectic transformations of this vector space. Because if you think of it as an SP2 theory, you can actually make this, don't just see the structure in the coordinates, but make it even more precise by realizing the symplectic group SP2NR, so of a 2 n-dimensional symplectic vector space, as the symplectic group of type SP2, so of a 2-dimensional vector space, but actually of a symplectic group of over non-commutative algebra. And I want to describe this shortly. So you take, I describe it in general and then tell you the example for which realizes SP2NR. So you take a non-commutative associative algebra, and the very important thing is that you want an anti-involution on this algebra. And using this, we define a symplectic form as it's a map from A, so A squared times A squared to A, which takes a vector in A squared and another vector in A squared and pairs them in the following way. I pick this somehow 2 by 2 matrix over A, right? Now you take the vector V1, V2, and you take its transpose, but you also apply your involution to it. And so then you define omega of VW to be this sigma of V transpose applied to this matrix W. This gives you an element. So this will give you an element in A. And so now you can look at having this symplectic form, you can look at the symplectic group over A sigma, just as linear transformations, invertible linear transformations of A, which preserve this symplectic form, just the way you would do it always. And so the way you realize SP2NR is in this way, by taking A to be the algebra of n by n matrices over the reals, with the involution or anti-involution to being given by the transposed. But of course, you can do more general things. So you can actually not just realize SP2NR in such a way, you can realize essentially all classical Hermitian symmetric space, Hermitian Lie groups of tube type. And I mean, you can even realize other things where, if you want to realize Hermitian groups of tube type, actually A sigma have additional properties, but you can also realize other groups as SP2A sigma without requiring the special properties of A. But in the case for the symplectic group, you have not just A, but you have this symmetric part, right? That you have always the fixed point set of this anti-involution. But in this situation, space of matrices, this is just symmetric matrices, right? You even have an open cone in this. And in this situation where you have this, you can actually do a lot of, I mean, now theory of SP2 over commutative fields like R or C, to do this over for SP2A sigma, where A is your non-commutative algebra. You can build models for the hyperbolic plane over A. And if you do this for this group SP2NR, what would you get? I mean, this is, so you get elements in the complexification of A, and they're the symmetric part, such that the imaginary part lies in this positive, in this open cone. And so if you do this in this example of the symplectic group, this would just be the standard Siegel upper half space model of the symplectic group. But you can do this in these, I mean, this more generous setting. You also get an action of this non-commutative SP2 on this space by the fractional linear transformation. And for example, one nice application of doing this, describing these models of the symmetric spaces, is that you get a model for you can do this also for the simplification, for the complexification. So for the complex group, get a model for the symmetric spaces. So it's the complex group SP2NC, which generalized the quaternion model for the hyperbolic 3 space, and which I haven't seen realized before anywhere in this situation. So now I want to end, and before I end, I want to go back to one thing which I mentioned when when looking at the Hitchin component. So you have different ways of looking at the space of G local systems of the representation variety. So I already basically implicitly identified these two sets, but if you fix a complex structure on the surface, you actually have a homomorphism to the space of Higgs bundles, and you have a lot of structure on the space of Higgs bundles, which gives you, which is very intriguing, gives you more structure to study G-local systems. And one is the Hitchin fibration, where you associate to a Higgs bundle a family of holomorphic differentials on your surface. And the Hitchin component, when Hitchin defined, was really defined as a section of this map. And I wanted to mention this because I think this is one interesting piece for open questions and conjectures, open questions with which I want to end. So the first thing I want to address, so I illustrated to you that this family of Hermitian Lie groups of tube type and the corresponding local system actually can be looked at as a non-commutative A1 theory. And so the other family, the SOPQ family, suggests that if you do something, can do something similar there, and you would actually get, when you do coordinates on the space corresponding A variety, that you would get a realization of a non-commutative cluster algebra for Bn. And if you do the exceptional family modeled on F4 roots as the Dinkin diagram, that you would get the non-commutative G2 theory. And we currently explore the Bn case with Zach Greenberg, Danny Kaufman, Merrick Niemeyer, and Eugen Gozilikov. And Zach and Danny are at Yale. So if you have questions about this, you should talk to them. Another question which I find very intriguing, also to address the question, what are relevance of this theta positivity in physics context, is whether there are some appropriate non-commutative versions of the Hitchin fibration, such that this set of theta positive representations, which looks a lot like the Hitchin component, actually arises in the same way as image of a section or a section of a subset of the base of these fibrations. And so then, two other questions I would like to raise. I already said, what is the relevance of theta positive in other circumstances? So this is, relevance independent of representation, so just for the structure on the Lie group, but also what are possible connections to the physics side. And the last one, we know that in Fock and Goncharov's work, there's a lot of interesting interplay between the tropical points of the X and A variety and the non-tropical points. Are there natural tropicalizations of this non-commutative cluster coordinates, for example, even in the A1 story? And with this, I would like to stop. Thank you.
Thank you, Anna. So let's take questions from the audience.
Thank you very much, Anna, for a wonderful and very inspiring talk. And I just want to make one comment as like a conjecture related to this. And for me, it was it came from your work and also this beautiful work of 5-author paper, Stephen Bradlow and 4 other authors, which and so in the case of split groups, there is notion of 4-dimensional quantum field series, which are called S series. So the physical counterpart of
Yes.
how splits Lie groups, and they define you need complex structure on the surface to define them. And I would conjecture that there is a 4-dimensional quantum field series related to each of the cases we discuss here. And I would place it related to this minimal SL2 triples in the Lie group. And it's a little difficult to say what does it mean 4-dimensional quantum field series, as far as I understand, but at least they have some features. Even mathematically, they may be not defined, but they have some features like space of vacua and like Coulomb branches and so on. And they're 4-dimensional, they have also 3-dimensional reductions. And so in the usual case, this brings us to, for example, to the Hitchin basins, to Hitchin fibration also. But I would also think that in these situations, kind of generalized S-class series, the analog of the Hitchin base, which does exist in this theory, explicitly exists in the work of Bradlow and other co-authors, and isomorphic to the set of positive points. So this complex variety should be playing the same role in this four-dimensional series as the usual, so relate to space of vacuums and so on. So this is just one instance. There are many instances where there are many features of this four-dimensional series which one can discuss, but I just want to mention one. And there is also the one related to set of positive points, which you can think about as a positive brane. But so my hope is that there exists this analog of classes series, which parameterized exactly by this data. And probably, as it follows from your talk, they have many other features which we hardly anticipate, but they should exist.
Yes.
Thank you very much. That's
Well,
great.
thank you. Let me just, there is this, in the work of Bradlow and others, there's this, you have this set of, in some sense, what I think should be part of the base of the Hitchin base, actually. Because if you look at, if you think of the Hitchin fibration being really defined for the complex Lie group, my expectation is that when you do when you find the right non-commutative version here, the base for the complex Lie group would be a bit bigger than this space, which Bradlow and others show that this parameterizes theta positive representations. But I would yeah, can I just, it's really, if there are people on the, so I'm really know very little about physics. I think the question about Hitchin fibration is important precisely to make connection physics. So if there are people on the physics side who would be interested in discussing about this, I would be very happy to do that. And if there are people in the US, so I will be spending my next academic year on the East Coast. So I would be very happy to, try to understand this better.
Yeah, but I just wanted to say that if one can try to say something with the answer yes or no. So I was thinking that the existence of this generalized classes series and description of the space of vacua using the Hitchin base, which already exists, this is kind of yes or no question. So.
Yeah.
Hi, I just have a question about the results you presented on for groups with theta positive structures.
Yes.
So are those proven based on the classification of those groups, those four families, or are they not?
Depends on, so actually, when so we are, so basically what you can, so most of the things are not using the classification. They just use the structure you use to give the classification. In some sense, so that I give you this list of 4 Lie groups, it comes from the fact of characterizations. When do you, if you have a reductive representation, when do you find a convex cone in the representation? And this has, you have, the representation has to be proximal and has to be even, and this basically gives you then conditions. And so most of the results don't depend on the classification, but you can also, basically what we also can show is that if you ask yourself, okay, so I have my unipotent radical of a parabolic subgroup, I want to find a semigroup which has certain properties. So for example, that the only invertible element is the trivial element. Then you're basically bound to these groups, which arise in the way I described them.
I see. So is it possible to generalize to, say, semi-simple groups to some extent? Or is
yes, yes, of course, but okay, on the Lie Ram, your semi-simple group is a, direct sum of simple groups, and then you.
Okay, thank you.
Yeah, of course.
And one more question, Anna, from the cluster side. You mentioned G2 non-commutative.
Yes.
So, and you didn't put question marks. This means that you know how to define these things.
No, I wanted to put question mark. So sorry. No. No, I think, okay, so, I would say it's question mark where I strongly believe that's there, and we have some ideas, but especially the G2 case, we don't have that yet.
But the B case you have.
The B case, we have a lot, I would say a lot of it. What we really want to, to really get the cluster structure, we are to really show that, we have basically, to really show that you can do arbitrary cluster transformations. We are still working on proving that. So there should be there should be a question mark actually. So this is, but for the BN case, we have a lot of the structure, but it's really BN non-commutative clusters arising from this setup, which means that you only have only the special fat node is non-commutative, right? And everything else is commutative. So it's not fully non-commutative.
Okay.
So hello. Yes, I have a question also. So you have extended total positivity from split group to non-split groups, but there's another extension in which split groups are replaced by like some G mod K by symmetric space. Such a theory also exists, and it's also generalization of this. And I wonder if that has only any connection with Teichmüller theory.
This I don't know, but I don't really know. It's a word. Where can I find something about this generalization where you replace the split regroup by the symmetric space?
Yeah, I wrote a paper maybe about 1 year ago or something.
Okay, so then I should look at it.
Yes, it's on archive. You can find it.
Yeah.
And it has the feature that so I think your theory can be defined also over semi-field, I suppose. Yes, over any semi-field.
Yes, yeah. Yes,
Well,
for the, in some sense, okay, so it's not, okay, so what doesn't, it's not complete, you have to have, what we really rely on is having these cones, but it's, I think you can use, you can define it probably over semi-fields, but for example, what is not completely clear to me is what I addressed in the fourth question, whether whether there's a nice way to connect this, for example, then with whether you can define some kind of tropical semi-field.
So it's not clear, because for this G mod K, you cannot define over any semi-field. You need from the tropical integers, you have to adjoin 1/2, I think. You have to allow 2 in the denominator. Then you can define.
Okay.
But anyway, that's all. Yeah.
Yeah, no, thank you very much. I will look at this.
Okay.
Okay, thank you very much. I think for the time being, we will stop here. So let's thank Anna again. Our next talk will resume at 11:40.
Oh yeah, you got it. Oh no, you got it. Yeah, this has to be. Thanks a lot, Anna. You still there?
Thank you. I will stay for the next talk.
Oh, great. Turn off the recording.